Okay, so good morning or good afternoon or good evening. It's really a pleasure to attend this event and to present this topic to you. I will start my presentation with types and requirements for chemical analysis. I will speak a little bit about the international accreditation of tests, and then I will discuss the motivation for develop this guidance and a little bit about the content of the guide. And then I will mention translations, and I will have some final remarks. Last one is rather provocative, I would say. Okay, so we all know that we can have quantifications or qualitative analysis in chemistry, measurements and examinations, and regardless of the type of chemical analysis, so we need to make sure that they are fit for the intended use, and so to be fit for that use, they must be based on an adequate reference. So both for measurements and examinations, and ideally, and then we have to be sure that they have affected by adequate uncertainty. So we have to make sure that the uncertainty is fit for the use of that determination, and ideally that uncertainty should be reported or at least considered in the results interpretation. So currently, the International Accreditation of Tests define that for measurements, labs must be able to report the measurement uncertainty, and they also must be able to take that uncertainty into account in the results interpretation. They can even be asked to quantify the risk of false conformity decisions, and so we have rather strict requirements for measurements regarding the uncertainty. But for qualitative analysis, the international community for the accreditation decided not to ask labs to evaluate the uncertainty from this analysis, and but labs must prove that the procedures, the qualitative analysis procedures, are fit for purpose. So they must be validated, and the validation concept for this specific type of analysis is, I would say, a more classical view of the validation concept, where uncertainty is not to be considered in that assessment. Eurachem and CITAC decided to develop a guidance on the assessment of the performance and uncertainty of qualitative analysis, because we have many relevant qualitative analysis being performed with a relevant socioeconomic impact, and there are lack of references to help analysts in checking if these analyses are fit for the intended use. In the document, we have definition. We select the definition of qualitative analysis. It is defined as classification according to a specified criteria, and these criteria should be as much objective as possible. Should be objective, and then the guide discuss that we can divide this qualitative analysis in three types. So we have qualitative analysis based on a quantitative criterion, like identification based on instrumental method of analysis, where you have a quantitative number, a quantitative value being compared with the threshold to support the identification, and in some cases the identification is based on a qualitative criteria, like color change that you can check visually. The guide also mentions that we have, I would say, a third type of qualitative analysis, that are the cases where we have a measurement result being compared with a specification limit or specification interval, and through this comparison, we state the conformity or no conformity of the tested item, and somehow we transform a measurement in a qualitative analysis, and this is only mentioned in Annex B because Eurachem and CITAC have guidance on specifically this type of assessment. But in Annex B, metrics that are used for the other types of qualitative analysis are also discussed for this specific case where we have a measurement value being compared with the specification limit. Okay, so in labs, regarding the management of qualitative analysis quality, typically we have two situations. We have cases where there is no regulation, no guidelines for labs to use about how to identify the presence of an analyte, for instance. And then what labs have to do? They have to develop the qualitative analysis procedure, and then they have to assess the performance of this procedure and define a classification criteria that should be successful enough or should produce false results, should produce a very low number of false results and very high number of correct results. And then we have other situations where we have our analytical field is heavily regulated, so we have regulated rules about how to identify the analytes, for instance, and then in this case the labs just need to follow the regulators' rules, but in this case the lab should prove that when applying that rules the success rate of their identifications is adequate. So they have to prove that that identification criteria work properly in their lab by implementing the procedure in their own lab. Also mention that the uncertainty concept is, I would say, applicable both to quantifications and to examinations, both to measurements and examinations. But when you have a measurement, typically the uncertainty is reported as a coverage interval with a specific confidence level. While for a qualitative analysis, the uncertainty is reported as typically as a metric that expresses the chance of incorrect classification, like a probability, a likelihood. So it is something different if we compare the coverage interval for the measurement case. So now I would like to spend a few slides on the content of the guide that was published in 2021. So first we have some introductory information in the guide. Then we have some information about the type of qualitative analysis, something that I just mentioned. And then you have a chapter on performance assessment, something on expression of confidence, how to report these qualitative analysis results, and then we have some conclusions and recommendations. We also have some examples in the guide. So the guide has some nice examples about how to apply the theory described in the guide to different types of identifications from different fields and different analytical instrumentation. And then we have some annexes with some more statistical details and explanations. So, like I mentioned to you, the guide describes two types of qualitative analysis based on qualitative and quantitative criterion. An example of the first type of analysis are detection of aliphatic aldehydes in a solution by color change by addition of shift reagent, because we check a color change. And then we have the quantitative criteria, for instance, for the identification of pesticide residues in fruits based on the abundance, quantified abundance of fragments from the mass spectra, and also based on retention times. So quantitative information. The guide also mentions this well-known information that typically qualitative analyses are of binary nature, or at least these are the ones that are covered, of course, in this document. And typically results are labeled as positive or negative. So, for the assessment of the presence of an analyte, a positive is typically evidence of the presence. A negative result is no evidence of the presence. And the rates of true and false results described in this document are reference to the number of positive or negative cases. So are related to the number of cases and not total number of results. The guide, of course, describes contingency tables. So the contingency tables are very well-known tools to report the performance of a qualitative analysis procedure, where you have where you know how many positive and negative cases. So samples where you know that an analyte is present, and items where you know that an analyte is not present, and then we assess how many of these cases get positive or negative results, and this gives us a vision about the performance of our qualitative analysis method or procedure. For instance, in this example that you see, so the procedure was tested with 233 positive cases and 301 negative cases. And for the positive cases, we got 228 positive results and 5 negative results. So 228 true positives and 5 false negatives, and 4 negative cases. In one case, we got a positive result, so a false positive. If we look to this table, we can calculate the true positive rate, for instance, and the false positive rate. The true positive rate is the ratio between the true positives and the number of positive cases. The ratio that will be 97.58%, and the false positives will be false positives divided by a total number of tested cases. In this case, 1 divided by 301, that gets 0.33%. One of important thing that I have to mention here is that these contingency tables are very informative about performance, but are not typically the information that we want to get when we analyze an unknown sample. So in this case, in a contingency table, our starting point is the case, and then we will get the result. So for instance, 97.8% tells us that if we have a positive case, what is the chance of getting a positive result? And typically, when we have an unknown sample, our starting point is the result, not the case. And we want to know what is the probability that given that result that we have a positive case. And this is a major issue when we look to this table. The guide also mentions that this quantitative table or this information can be collected through experimentation. So we can quantify the false positives and false negative rates experimentally, like in the example that I just mentioned to you. But experimentation is not very convenient to deal with this table when we have low rates. For instance, imagine that we have a false positive rate of 0.5%. We need 0.5% false positive, so we need to test at least 598 negative cases to have 95% chance of observing at least one false positive. And if we want to increase the confidence of this observation, we will need to have 919 negative cases being tested to see one false, at least one false positive. And this is a big limitation because, in fact, if we want to quantify these false result rates in a reliable way, we would need 5 times more analysis of negative cases to get these numbers in a reliable way. This limitation is important in some fields where we have very expensive analysis and not so many samples available. But we can somehow overcome this by using alternative tools to experimentation, like using reference databases. For instance, if you want to assess our FTIR identification method, we can set a match between a reference and the unknown spectra of the unknown item. We can get a minimum match, and then we can check the adequacy of this match by comparing a reference with different spectra from this database. This is a way of checking somehow the performance of this spectral comparison methodology that includes a threshold for the match, but has a big limitation because typically the population of the database does not match the population of test items. We have one spectra of different species, and typically the population that is being tested, like environment, sediments, we don't have such a diversity, and you have many examples of one of these types of spectra because we have many chances of getting many times one of these species. So this is a big limitation. Another option is to do signal modeling. So, for instance, in GCMS identification of trace levels of compounds, we can simulate signal noise. We can simulate the distribution of abundance ratios, and you can simulate the chance of a signal noise producing abundance ratios that suggest wrongly the presence of the analyte. So the handling of these low false results rates is difficult, but there are tools available, in particular modeling, but the modeling must be sound, of course. The guide also discusses the expression of confidence. It highlights two metrics, likelihood ratio and the posterior probability that I will mention later. Likelihood ratio is a metric that you can get it from Bayes' theorem, I would say, that for positive cases, it's ratio between true positives and false positives. And this metric express a ratio of two performance parameters when the analytical method is applied to positive and negative cases. So it is in fact a ratio of two performance parameters. And this makes the interpretation of this number more difficult. But if we assume that positive and negative cases are equally likely prior to the test, so if you assume that positive and negative cases have the same frequency, I would say, or are equally likely, then we can look to this number, for instance, 7,600, as saying that a positive result is 7,600 times more likely to be true than false. And this number, or this, if we assume this assumption, is easier to handle this number. This metric is very popular in forensic analysis, and they have a nice table where they transform a likelihood ratio in a verbal equivalent that they can use in court, for instance. If we take the example of 7,600 for likelihood ratio for specific evidence, they say that we can claim that evidence is a strong support of the first proposition rather than an alternative one. And this somehow helps communicating information about how strong is the evidence that is being provided. And this is, of course, very important because a positive result can be supported on weak or extremely strong evidences. Another metric that is mentioned in the guide is the posterior probability. The posterior probability of a sample being genuinely positive for a positive result, of course, is being mentioned. First, let me tell you that this is exactly what labs want to know. When we have a known sample and you want to confirm the presence of a compound there, we get the result, imagine a positive result, and we want to know the probability that the sample having genuinely the analyte present there. And the calculation that can be done to get this posterior probability also from Bayes' theorem is this formula where we have the likelihood ratio there. But we also need the prevalence, and this is the tricky part of this metric. So we need to know in advance the prevalence of positive and negative cases. So we must know information about the population that is being assessed, how many positive and negative cases are there. For instance, if we decide to assume that we have 50% positive cases and 50% negative cases, and if you apply in this formula, the posterior probability will be 99.987%. If we assume, because we know from the past or from previous records that positive cases are unlikely, in this case 0.5%, and negative cases are more likely, then the posterior probability gets to 97.4%. Okay, imagine this could be, this probability could be imagined if we take a specific sport competition, 0.5% can be the percentage of urine from an athletes that were confirmed to have cocaine in the past. And no cocaine are the other ones, and we can use this information to get the proceed probability. The tricky part is to make sure that this probability is applicable to our scenario. The guide also mentions how to report the result with this uncertainty. It clarifies that the information must be clear and sound. This should be, sorry, this is 10 to 4, okay. And in this case, we have cocaine is present in sample, and then it is reported likelihood ratio. And we can also, we have an example where you have the probability, proceed probability being reported with a positive result, and it is stated something about the assumptions about the prevalence. Currently, accreditation is not asking for this type of reporting. So the guide closes with some recommendations. It is stated that laboratories need to check at least most critical false response rates. Laboratories are expected, of course, to follow adequate practices and available regulation for this analysis, and also mentions that reporting this uncertainty as a numerical value must be careful to avoid misinterpretation. The guide also has some examples from identification by GCMS, infrared, immunoassay techniques, PCR, and these examples are very useful to understand how this applies to real world problems. This document was already translated in 4 languages, and I have my final remarks. Nowadays we still have some analytical fields where we have problems in some qualitative analysis. So qualitative analysis are relevant, and in some areas we have needs to improve, and the assessment of the performance, even transforming it in a qualitative analysis uncertainty, can guide us to understand which analytical procedure must be improved. And then to close that provocative thing, so I asked ChatGPT, about what will be the future of this concept in accreditation. So ChatGPT knew that currently accreditation is not requiring the quantification of the uncertainty of qualitative analysis, and then I asked, according to the international accreditation, how this international accreditation has evolved, when do you think that the reporting uncertainty in qualitative analysis will become mandatory? And then ChatGPT said, you can check yourself, that mandatory reporting may not be universally applied in short term, okay, but sectors where qualitative analysis results have critical implications, like forensics, environmental compliance, and health, may be among the first to require it, and it is stated likely within the next 5 and 15 years. Okay, very short term, to be honest. We all know that this concept is important, but we also know that labs should only ask to apply it if they have the tools for doing it. Thank you very much for your time.